Hey everybody. So this is going to be a little, let's call it an introduction to a review of functions. So this is intended for the beginning of a calculus class. So my expectations are, if you're watching this, you have some experience with functions. If you thought pretty hard, you would be able to come up with some kind of definition of a function. You should be familiar with some functions. But I want to go through some of the basics because in calculus, functions are the things that we play with, right? In math, most of math up to this point, numbers are the things that you've played with, right? You learn to add and subtract and divide and multiply numbers, and eventually you learn algebra where you let letters represent numbers, but you're still really manipulating numbers. And now, as we move forward, functions are going to be the thing that we spend a lot of times manipulating, right? You've seen a little bit of this. You've probably seen how to add functions or compose functions, some of these operations or transform functions. But we're going to learn some more complicated things to do with functions. So we need to have our understanding of what a function is and how we use function notation down pretty tight, because that's going to be the stuff we're working with. And so we have to have that base solid. So let's go through quickly. Again, I'm expecting that you've seen some of this, most of this before, if not all of it, and have some familiarity. So a good way that we think about functions, right? Or one way we might think about it is it's a little machine that takes an input. Right, you drop this into your function machine. I'll give it an F for function, and your function spits something out that we call the output. Okay, right, and there's a couple rules that we want on this. If we put the same input in, we'll get the same output out, right? You wouldn't put an input in, put the same input in later and get a different output. It does the same thing every time. Our function is consistent. Some examples of functions. Right, I could set up a function, right, and this is what a function is. It's a thing that takes an input and gives us an output, and for each input it will only give us one output. Each time it will give us the same output, right? So we could have a function, for instance, where our input is the date and the output, right? The function might just tell us, did it rain on that day? So the output would either be yes or no, rain on that date, right? So maybe this looks at some historical data. You tell it some, April 23rd, 1972, and it will tell you whether it rained in Seattle on that day, okay? And that's all that function is. So each date will either have a yes or a no. And if you put in the same date again, it should tell you the same answer, right? That it shouldn't change whether it did rain on that day in the past or not, right? Another function might be we take the name of a person and we output the day of the week they were born on. Right? So I don't know what day I was born on, but if this was the function and you put my name into it, out comes Thursday, and somebody else puts the function in, out comes Tuesday, and somebody else puts it in, maybe they were also born on a Thursday, so out comes Thursday, but each person was only born on one day. And so for each individual, right, so let's not worry about things like repeating names. We'll have some kind of designation for each repeated name, but each individual was born on exactly one day. So there's no time you're going to put in a name and then later put that same name and get a different day of the week. You might go into a shipping company with a package, and they determine they look at the package weight. Let's assume some kind of standardized box, and out comes the cost to send that, right? That would be a function. Input the package weight, output the cost to send it. Or if you were managing a truck driving company, you might be interested in a function where the distance you have to ship something, have to drive something, the gallons of gasoline needed to get there, okay? So most of the functions that we use are going to be, actually all the functions that we'll typically use in a calculus course are going to be functions where the input and the outputs are numbers, right? Maybe they'll represent something like what I've done here. Maybe they'll be more abstract, just some mathematical function where we input a number, do something to it, we get a new number out, but that's still our input output, okay? So let's focus on those kinds of functions, okay? And here's a very typical notation. Well, let's put a couple notations in here. We'll often name our inputs. So X is a common name to give to the input. You can name it anything you want, but X is a very common one. F is a common name of a function, and we represent the function doing what it does to the function, to the input like this, right? So F is our function, and we put X into it, right? We put that input in, and often we'll name the output Y. Okay, so this is another way to look at this, right? We put our X into the function F, and out comes F of X or Y, right? So you'll often see Y equals F of X. Let's look at this more closely. The F of X and the Y are really the same thing. These are both representations of the output. And again, these particular letters aren't important. What's important is that who's ever writing for you makes clear the names, what are the inputs, the outputs, the functions, and so forth. So in this case, we're using both the symbol F of X, this entire collection, the F with the parentheses and the X in the middle, that whole thing is one way to represent the output, or we might just represent it with a new letter, okay? Sometimes you'll see people use the letter Y for both the output and the name of the function if they want it to be a little more consistent. Sometimes they make it separate if they want to. It's difficult to say exactly why that might happen, but sometimes it can make things clearer. Sometimes it's just the author's habit. So you have to get a little bit used to the fact that these letters might not always match. The X, again, this is our input, the X by itself, right? So these are the pieces of our function notation, okay? So I mentioned earlier that one way we think of a function is we take an input, we put it in, and it's a little machine that does something to it. Another way we can think about this is a function is a set of instructions, right? Each of the functions that I gave in the example can be thought of that way, right? If you give me a date, my instructions are to go to whatever historical data I have about the weather in Seattle and look at that to find out whether it rained or not. Or if I have your name, however, I'm going to figure out, I maybe look up your birth date and then go and figure out from a calendar what day of the week that was. Each company might have a set of instructions, right? Maybe the instructions are just up to a certain weight, it's one cost, up to the next weight, it's another cost, but that's still a set of instructions to look at their chart or whatever it is for each weight and find the cost. And same thing for a distance, right? That can be determined knowing some things about the truck, the weights, it's probably a more complicated set of instructions, but there's some set of instructions that you can use to determine this. Mathematically, when we're dealing more abstractly, we'll often write these instructions with mathematical symbols, right? So if I have a function f of x, and I say f of x is equal to 3x minus 2, what I'm telling you is that this is the function that tells you to multiply the input by 3 and then subtract 2, right? And so in practice, when we want to actually do something, to actually see what a function does, so if I wanted to take this same function and compute f of a certain number, like let's say f of 4, right? So I just simply take that input, multiply it by 4, and then subtract 2. Right? So the common way we think about this is, right, you look at your x I've replaced the X in the input with 4, so I replace the X in the set of instructions with 4. Okay, that's what that function does. Right? Some functions mathematically have more complicated sets of instructions. Right, g of x, so I'm calling my function g, and this is the function sine of x, which in itself is the name of a function. This is a much more complicated function, right? If you remember your trig, I'm not going to try to go through the whole definition of sine, but remember you start with a unit circle. Draw a unit circle, you trace an arc, starting at the point 1, 0. Oh, I should say draw a unit circle centered at the origin. Trace an arc starting out at 1, 0 in the counterclockwise direction. Draw a ray from the origin to the terminal point of that arc. And let's just say determine the y coordinate. Oh, I guess I didn't need to draw the ray. But anyway, you determine the y coordinate of the terminal point. We usually draw the ray because we're dealing with angles and we get our little angle there, but we didn't really need it. You look at the y coordinate of that point on the circle, right? So that, of course, is it's not how we often compute sine, but that's by its definition what the set of instructions are. It's a pretty complicated thing. We don't usually have to do that, right? We let our technology work for us, but we can compute. We know some of these. G of pi, for instance, is sine of pi, which turns out to be 0. Okay, so these are a couple of examples of these more mathematical functions. Inputs are numbers, outputs are numbers, and we have these ways to represent them, right? So this is one way to represent the functions. Both of these representations, without explicitly giving you what is the output for each input, does implicitly tell us what the output for each input is, right? So for instance, I don't know what f of 2,395,425 is, but I know I can do it, right? If I had to do that, I could multiply that by 3 and subtract 2. So all the information's there if we want it. We know every relationship between an input and an output. There's 2 more ways we represent functions, which is what I want to finish this video with. And let's look at a simpler function to do this. Let's call this function, let's use different letters to get used to that. Let's call it p of t. And let's say this is the function t squared, right? So in other words, this is the function that says, given an input, multiply it by itself. And then report the result. Okay, so presumably we are familiar with this function to some degree, but let's use it to see how we can represent functions. And let's represent this function with a graph. So I'm going to draw myself a set of axes. Since I know what this function looks like, I'm going to be convenient in how I draw my axes. So let's call the horizontal axis the t-axis, and the vertical axis the p or p of t axis, right? So instead of the x and y axis, because those aren't the variables I'm using, we should start thinking about the horizontal axis as the input axis and the vertical axis as the output axis. Okay, so let's pretend we don't know anything about what this function looks like. I want to make a graph of this function, right? Well, we have to say what a graph is. Okay, so given our standard, I won't go through how a coordinate system works, but we have, right, we can imagine there's a scale on this. I'll just use the dots that are here. If you can see those dots, there's Maybe I'll put in a couple just to get an idea of the spacing. We'll let each of these dots represent a unit. So the way a graph works is as follows. Let's make a table to do a couple of examples to be clear about how a graph works. And you probably have seen this before, and I think I know how a graph works, but I feel like often at the beginning of calculus, we think of graphs of functions as pictures that are labeled by the name of a function, and the actual connection between a graph and the function is a little bit lost. So I want to take a little bit of care in doing this. Let's evaluate this function for a few values. So I'm going to list some input values here, also -2, -1, 0, 1, and 2. And then of course, P of t, I could have also written t squared, right? Because that's what happens in this column. I'm just putting the output. So all I'm doing is squaring each number. So -2 squared is 4, -1 squared is 1, 0 squared is 0, 1 squared is 1, 2 squared is 4. So here we have a table of some of the values of this function, these inputs and outputs. The way we translate this to a graph is that each of these can be represented as an input-output pair. So we write our input, then our output, our input, and our output, our input, our output, input, output, input, output. And we treat these as coordinate points, right? So the point -2, 4 is right here. The point -1, 1 is right here. 0, 0 is here. 1, 1 is here. And 2, 4 is here. Okay. Now, this gives us maybe a hint of what this looks like. Again, I know we're probably familiar with it, so we know what it looks like. But in reality, we would have to do a little more work. But we can, let's play pretend. We could do 1,000 more of these and get a much more detailed picture. I could do -3, -4. I could do -2.5, -1.1, 2.7, all these different numbers in between. And what we would end up with is, we see all the points that start coming out. We'd end up with this shape. All right, my drawing's not great, but we end up with a shape that we kind of recognize as a parabola, right? Make sure we understand this connection. Each point on here, so I think I got this right, 1, 2, 3, 4, 5, 6, 7, 8. Oops, I missed it. Should have gone through this point here. I couldn't count and draw at the same time. Each point on the graph, when I draw this line, what I'm representing is all the points that are input-output pairs, such that the first point, when squared, gives me the second point, or the coordinate. The first coordinate, when squared, gives me the second coordinate. Okay, and any point not on the graph is a point where that's not true, right? This point is not on the graph because when you square 3, you don't get 1. Okay, so that's what this picture is. Right here, we have 2 more ways to represent a function, right? We have a graph, which is a visualization of every input-output pair, right? I did 5 of them in this table, which is another representation of this function. The graph has the advantage of, a graph is like a really nice big picture. We lose a lot of detail. I can't use this graph and figure out what -2.3 squared is by estimating where that line goes, right? My line's not good enough, and even if it was a perfectly done graph, I would have a very hard time estimating it perfectly. But it gives me a really good big picture idea of what the function does, right? I can look at this thing and see, well, for instance, this function doesn't appear to ever go into the negative numbers. It appears to grow larger and larger as we get farther away from the origin. Things like that are clear from that picture, okay? Tables are not as useful for this kind of function typically, right? This function has an infinite number of inputs, and writing out an infinite table would be incredibly inconvenient. But sometimes, if we are trying to determine what a graph looks like, graphing a few points can start to help us get a sense of it, right? You can always fall back on that if you're supposed to graph something. You don't just have to remember it from somewhere in your past. All right, I think that's all I want to say in this video, except to just redo this graph with something a little nicer. So here's a graphing program that I use often called Desmos. So here, it's going to be the same thing. There's the 4 points we just plotted, but here I'm doing it with the computer. You can see they have the same table. And then here's what that graph looks like. If we start to zoom out, we get a bigger and bigger picture of what that graph is. Okay. One last thought. When you see me plug something like this, plug this function into a much nicer graphing program than what my hand can do, an obvious question is, why would we ever bother graphing by hand? I simply want to encourage you at this point. It's really valuable. It's really valuable to spend some time doing this. If there's a function you're not that familiar with, plotting points to see how it leads to the graph that maybe you can look up somewhere or let something like this do for you is a really good tool in building what we often call intuition. I think sometimes people think that intuition is this thing that we have that's natural, but intuition is something we build through work, right? And having intuition about functions is really crucial to be able to work and solve them. I know that we don't need to graph by hand. I know that we have computers that can do it for us, right? The process of graphing by hand lets us do the things later on that computers can't do, right? To look at a problem that's never been done before and have some ideas about how we might proceed because we understand the way that functions work. It won't feel like that in the beginning, but I have a hard time imagining a person for whom this process doesn't lead to better, what we call intuition around the functions and the ideas that we study in mathematics. Okay, I should stop talking now. Thanks, everybody. I will see you next time.